Example 5-3 is about the trapezoidal channel with the bottom width of B0 equal to 5 meters and sidewall slope of 2 horizontal to 1 vertical. And the longitudinal slope is very mild, it's 0.04% with the Manning's coefficients of 0.02. The normal depth in the channel is 3 meters, so normal depth is given. And then with the slope, Manning's coefficient, and the dimension of the channel, we would be able to use Manning's equation to calculate discharge. And once we get discharge, we can calculate critical depth. And the water level gradually decreased to a water depth of 1.25 meter. So the question asked to calculate critical depth, calculate the gradually vary profile using direct step method, and then they calculate the distance between two sections having the depths of 2.3 and 2.8 meter. So here is a schematic of the trapezoidal channel. So we convert the channel slope from percentage by dividing by the slope by 100. Normal depth is provided, so we use a Manning's equation. And when you use Manning's equation, cross-sectional area and hydraulic radius can be calculated. You have the slope. The only unknown is discharge. Then we go and use the Excel file. So in the Excel file, we are going to set up the columns to calculate using the direct step methods to calculate the distance. So we have the normal depths, bottom width, sidewall slope, longitudinal slope, Manning constant. So we calculate the discharge using Manning's equation. So here is the discharge, 48.68. And we also calculate a critical depth. So here is the Fruit equation, discharge to the power of 2 times top width divided by acceleration due to gravity times area to the power of 3. So that gives us Fruit squared to the power of 2. Now I start with 1. So its Fruit number is larger than 1. So 1.6. So I change it to 2. So it's less than 1. So the critical depth should be between 1 and 2, maybe 1.5. So less 1.4. So 1.6, yes, 1.7, 1.65, very close, 1.67, 1.68, 1.685, 1.69. Yes, so 1.69 gives me Fruit square equal to 1. So this is the Fruit number. This is the critical depth. And now I'm going to set up the columns. The first column is the depth, and then cross-sectional area, B plus my times y. Hydraulic radius is area divided by weighted parameter, B plus 2my, 2y square root of 1 plus m square. Then we calculate velocity, discharge divided by cross-sectional area. Then we calculate friction slope, which we use Manning's equation and rearrange Manning's equation. So it's going to be q square times n square divided by area square hydraulic radius to the power of 4/3. So we calculate friction slope, and then we calculate specific energy, which is y plus v squared divided by 2g a squared. So q squared divided by 2g a square. Yeah. Or we could have used v squared divided by 2g. It gives us the same value. Now I'm going to reduce the depth by 5 centimeter. Then we do all the calculation and we'll get the distance. So in order to have a 5 centimeter drop in water level, it takes almost 3 kilometers to lose 5 centimeter. And now I can drag all the data to get the distance. So what you need to be careful is that in some cases that you're using dimensions, you need to use a dollar sign to make sure that as you drag the data, the dollar signs holds the values in their place. And also here we calculate the average slope. So the average slope is the slope between two adjacent distances. So 1/2 of the friction slope between 3 and 2.95 depth. And then the longitudinal slope or the channel slope minus the friction slope, the average friction slope. So then we can calculate the energy loss. So we have the energy difference between two sections. So we calculate the energy and then we calculate the energy difference. And then delta X is equal to different energy divided by a different slope. So you see here that I use a negative sign here because I want to have distances positive. Okay, so it means that I use that negative sign here to show that the direction of the distance measuring from one point is different from the direction of the flow. Okay, so as we go downstream, distance is positive, whereas as we go downstream, the water level drops. Okay, so we can keep continuing reducing the depths every 5 centimeter, and then the distance will be calculated. So we just drag this to see how far we can do the back calculation, and you will see that as we go further and further, the drop in water is still 5 centimeter, but the distance or delta X reduces dramatically. So you'll see that delta X in the first 5 centimeter drop of water level is 3 kilometers. But then from 2.95 to 2.9, the second 5 centimeter, it happens only in 970 meter, and then 550. And then you will see that from the water level dropping from 2.1 to 2.05, it only requires 19 meters. So as you're getting close to critical depth, you will see that it takes less and less distance. And then you reach to the point that the distance becomes negative. And that's exactly at the point that you have critical depth. So you see here that we calculate the critical depth and it's 1.69. And here, right at 1.7, we have positive value. And then here, if I change this one to 1.69, you will get a distance close to 0. So this means that the Dirac-Estab method can be also used to determine or to double check the critical depth. So now you have all the increment and distance, and you can answer the questions for part 3. So calculate the distance between two sections having a depth of 2.3 and 2.8. So if you go back, here we have 2.3, and then here we have 2.8. So the distance here is 4.9, 4,934, and the distance here is 6,100. So what I need to do is I just need to subtract this 2. Okay, so the distance between 2.3 and 2.8 is 1,243 or 42.9 meters. So, and then you can also plot depth versus distance to answer part B. Okay.